Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8, 2025, just yesterday. It introduces a new fine-tuning method that achieves over 91% accuracy on a key reasoning task, while using only 60% of the parameters of other methods. The paper is titled SingLoRA, Low-Rank Adaptation Using a Single Matrix, and the implications for model training are quite significant. It addresses a core instability in LoRA, a popular method for efficiently fine-tuning large models. Also, the authors shared their implementation on GitHub, and it's a wonderfully minimal repository. You'll find a single file implementation, which is great, and it even includes ready-to-go examples for applying SingLoRA to models like Distilbert and Llama, making it very straightforward to try out for yourself. Alright, so moving to the results. This first table really highlights the core improvements. It compares their new method against several existing techniques for parameter-efficient fine-tuning, which is a way to update just a small part of a model to save on computation. It's benchmarked against methods like low-rank adaptation, or LoRA, which usually adds two small matrices to update a model. Looking at the Roberta and GPT-2 results, the new SingLoRA method consistently matches or beats the accuracy of the others, while using about half the trainable parameters. A really significant efficiency gain. Building on those performance numbers, this next plot helps explain why the new method works so well. It shows a convergence plot from a synthetic experiment. On the vertical axis, we have mean squared error, which is just a measure of the model's error, where lower is better. You can see that the blue line, representing SingLoRA, drops much more steeply and reaches a far lower error than the standard LoRA method. This demonstrates that it converges, or learns the task, much faster and more effectively, highlighting its superior training stability. This next plot really drives home that point about stability. It shows the accuracy of a Llama 7B model on a reasoning task, but tested across different learning rates. The learning rate is a key hyperparameter, which is a setting you have to tune to get good performance. You can see the solid line for SingLoRA stays consistently high, only fluctuating by about 1%. In contrast, the dashed line for the standard LoRA method is all over the place. Its accuracy drops off a cliff at a higher learning rate. This robustness is a huge practical advantage. And this next table provides another powerful, concrete example of that advantage. Here we see the results of fine-tuning a Llama model on the MNLI dataset, which is a common-sense reasoning task. SingLoRA achieves the highest accuracy at 91.3%, beating all the other methods. But the really striking part is the parameter count. It gets this top score using only 12 million parameters. That's roughly 60% of what the other methods need. This result really drives home the core claim: superior performance with significantly greater efficiency. Okay. So, we've seen how well this works for language tasks, but what about images? This next figure shows a qualitative comparison on DreamBooth, which is a popular technique for teaching a model to generate images of a specific object or style. You can see the original object on the far left, and then the results from different methods trying to place that object in a new scene. Across the board, whether it's the teddy bear or the cat, the images generated using SingLoRA just look better. They're more coherent and faithful to the original subject. And this table really quantifies the improvements we just saw. It's showing performance on DreamBooth, measured by a few similarity scores where higher is better. The key takeaway is how SingLoRA performs. First, when using half the parameters, just 0.45 million, it's already competitive. But then, when given the same parameter budget as the other methods, it achieves the best Dino similarity score, which measures image fidelity. This result shows it's not just more efficient, but can also be more effective when given the same computational resources. So to wrap things up, this new SingLoRA method offers a really elegant solution to a core problem. Standard LoRA can be unstable because it uses two separate matrices that can get out of sync during training. By using a single matrix and its transpose, which is a kind of mathematical reflection of itself, it guarantees stability by design. This transformation invariance makes it incredibly robust. So you get a method that uses about half the parameters, but consistently delivers better, more stable results across the board. That's all for this week's AI Research Roundup. Thanks for tuning in.